what I'm going to talking about is a new modeling method we released less than a year ago with JMP Pro 17 that will allow you to modeling random effects and the fixed effects for binary and the count responses. So let me first talking about when you want to consider using this generalized linear mixed models, GLM, and why you should consider using it opposed to other standard regression methods. So here is an example, and that I will demo. So in this example, we are inspecting manufacturing defects from the lots that are randomly selected. And also within each lot, we also randomly select units. And the response is number of defects. They are integers, 0, 1, 2, 3. And the treatment effect or the fixed effect is the finishing amount, the finishing treatment amount. So here, when we want to estimate the effect of finishing treatment amount on number of defects, and we also want to consider or account for lot-to-lot variation and also unit-to-unit variation. So that's our objective. So here, the standard methods are not the right choice of the model when you're dealing with data like that, count data, and we have random variation between the lots and between the units. So let's just compare to a few models you are familiar. So ordinary least squares. Now, ordinary least squares assuming normal errors, and also the response variable is continuous. So you, in this case, the ordinary squares methods are not appropriate. Now we have a linear mixed models that allows you to account for the random variation. But the linear mixed models, or the mixed model we call in JMP, assuming, again, normal errors and the continuous response. In JMP, we also have, in JMP Pro, we also have a generalized linear models that allows you to model the response that are not continuous, that are counts, that are in binary form. But the GLM or the GenReg, as we call in JMP, does not allow random effects. So the new GLMM platform combines the linear mixed models and the generalized linear models for modeling in the initial release, for modeling counter data and the binary responses with mixed effects. Let's talking about what we have. So here just is when you should consider using GLMM and why you should consider GLMM over standard regression models. Now, what's in GLMM? As I mentioned, this is a brand new platform released last fall. So in this initial release, we support two distributions, binomial distribution and the Poisson distribution. You will expect more features, more probability distributions, and repeater structures in the future release. We are actually actively working on JMP 18, JMP Pro 18 to be released sometime next year. And I should also mention generalized linear mixed models, just like the linear mixed models, is JMP Pro only. Okay, so this is my quick introduction to this new platform. Now let me continue with this count data response example. So here is the data set. So we have 18 randomly select lots. Within each lot, we randomly select 6 units, subunits within a lot. We inspect for the defective products, and we also have this finishing treatment amount information. And this is where I'm gonna go fitting my model. Go to the analyze fit model. So first of all, this is my response, and this is my fixed effect. But here, I'm gonna turn on the GLMM modeling personality. That will have the random effects tab. So I'm gonna consider the lot-to-lot random variation. And I also consider the variation, the random variation from the interactions between the treatment, between the finishing treatment and the lot. And I'm also adding a unit to unit variation. Now, since the unit is not uniquely labeled, it's only uniquely labeled within a lot. So I would have to using this nest to making sure the unit ID is uniquely identified. So I'm just gonna do this. Okay, so here I have 3 random effects, and also this my fixed effects. And I'm gonna switch the distribution. So there's 2 distributions available. I'm gonna switch the distribution, the default, the binomial to Poisson, because I know my response is integers. And I'm gonna fit in my model. So here I have my model results. So let me just go over the key outputs here in the report. First of all, this just confirms it's a Poisson distribution. And with the Poisson distribution, just like in the generalized linear models, we're modeling actually the log of the response, log of y. In this case, it's log of the number of the defects. And another key information you want to pay attention to is this generalized chi-square divided by degree of freedom. Now, this gave you some indication. You would like to have this number to be around 1. If you see a number that's very large, greater than 1, 5, 6, 7, or 9, that might indicate there's some over dispersion in your data set. That perhaps is because of the Poisson distribution that we are using. Since in the Poisson distribution, the mean is equal to the variance. Only one single parameter determines the shape of the distribution. So in this case, I have 1. So I don't have that problem. This is the random effects part of the results. So I'm just looking at the water p-values just to see if there's a significant random variation. So here I see it does show there is significant variation between units. However, for the between lots and for this interaction, the p-values suggest the variations are not significant. Now I could run another model by dropping lot and the lot times finishing treatment. I can drop these 2 random effects and keep this unit as the random effect. I did that. The results are similar, but for today's set, the presentation set, let me just keep this this model specification. Okay, so we know that we need to control, we need to adding the unit as a random effect. Now let's talking about this fixed effect. This is similar to a generalized linear model. So here, since we're using by default, there's a log transformation, the interpretation of this coefficient is in terms of a percent. So this tells me with 1 unit increase in the finishing treatment amount, you're going to expect to reduce the number of the defects by 16.7%. That's what this suggests. Now, sometimes you do not want to have the percentage, and you want to see what's the actual reduction of the number of the defects by increasing the amount of my treatment, finishing treatment. And there is a profiler that you can use. So in the profiler, it converts the log back to the original scale. So here it shows at 5, I'm not sure exactly the unit of a finishing treatment amount. Say at 5 units of a finishing treatment, you're going to expect to see about 8 defects within the 95 confidence limits, showing the blue numbers. And you can also see how about I increase the number, increase the amount of a treatment. You're going to expect to have a lower number of the defects. So this way for you, it's a log. I don't want to have the log interpretation, the percentage of the interpretation, and you can use this marginal model profiler. And as you know, in modeling platform, you can also to save the predictions. So here this is the same with most of the modeling, the regression model platform in JMP. So you can save the predictions for each row in your data table. So this is basically the default, the key results, and there's also multiple comparison. I mean, you can perform as you do with the standard least squares or GenReg or mixed models. You can also do the multiple comparison, and here are a few comparison methods like 2 keys methods that are available to you if you wanted to compare, do the comparison. Now, I wanted to show, as I mentioned, that the key reason is we wanted to account for the subject to subject or between subject variation, right? In this case, we found that the unit to unit variation is highly significant. So what if I do not adding units as a random effect? What will happen? I just want to making a comparison. So let me drop this. I still keep these 2, so we can have a comparison. So I run that, and as you see here, as I mentioned, that the generalized chi-square divided by degree of freedom is indication of over dispersion. You mean you have more variability than you expect. So here you see this is a 1, here is a 5.7. When I added the units, subunits as a random effect, I basically address the over dispersion problem inherent in the Poisson distribution. I just want to making sure, here is also the difference that you can see between a GLMM and a GLM. Okay, so this is my first example. As I said, right now there's 2 distributions are available in GLMM. The other one is a binary distribution. And here I'm going to show 2 examples because in JMP we can handle 2 different types, different data types for binary distribution responses. So the first one, I call this as a group data example. And here is the situation. Say We randomly selected the 15 clinical centers. They are participate in clinical study. And in each clinical center, we randomly assign the patients into 2 treatments. Let's call A and B. So center 1, we have 32 in treatment group A, and we have 33 patients randomly assigned to treatment B. And what we wanted to analyze is what's the probability. Here is the example. We wanted to analyze the treatment effect on the probability of a patient reporting a side effect, a severe side effect. Now, the data are summarized, are aggregated by the individual patient data. So right now we see is at the center level. So for center 1, from the patients assigned to treatment A, 14 of them reported experiencing severe side effects. And in treatment group B, 18 of them. So that's why we call this a group, a summarized data set. Now, this actually is the form of a binomial distribution. Recall that the binomial distribution we always characterize as K success out of N trials, or K values, in this case, side effects out of N trials. So we have 14 events out of 32 patients, 18 events out of 33. So this is actually a binomial distribution format. Okay. Now, why we want to using the GLMM? Again, here in this data set, we don't have patient demographic information, age, what's their pre-physical condition, anything. So we can using the GLMM to account for the center to center. I'm sorry. In this case, we do not have the information regarding the center, right? Urban, rural area, suburban. We do not have that information. And since these centers are randomly selected, and we can using the GLMM to account for the center to center variation between center. That is, we're gonna add a center as a random effect. Okay, so here is the data. It's a very simple data set. You saw. Go to the fit model, and here is, in this case, you're gonna choose 2 variables as your Y variable, K out of N, K events out of the N trials. And this is my fixed effect. Now I'm gonna switch from the default standard least squares to GLMM, and I'm adding center as my random effect. And here, yes, that's a binomial distribution. And click OK. I got my results. Again, this generalized chi-square by DF is 1.09, so it's around 1, does not indicating over dispersion problem. And again, for the logistic, this is a logistic regression, and the link, the default link is logit. We are actually modeling the log of P over 1 minus P. P is the occurrence. P is the probability of reporting side effects. So that's same thing for all the logistic regression. But here, just showing you where you are estimating the logit. This is now in this case, we do not see a significant variation between centers based on the p-value. I would say marginally significant. since the p-value is 0.05. If we're using 0.05, it's marginally significant. It's not like a totally a wash. It's marginally significant. And here is the results. Now, since the treatment is a categorical variable, right? We have A and B. I actually would prefer to using the indicator parameterization estimates. Now, this option is not new. It's not only available in GLMM, it's available in standard least squares. So this is just a better interpretation. So here, what we're looking at is the log odds ratio. Why log odds ratios is the link functions logits. We're looking at the log odds ratios between the treatment group A and the treatment group B. The default actually compare the log odds ratio between the treatment A and the average treatment. So I prefer this indicator function parameterization. Sometimes it's called the dummy variable coding interpretation. I prefer that. So you can report this, this is acceptable in the pharmaceutical industry, in the clinical study. You say, I found that the log odds ratio between the two treatments is negative 0.489. Or you can exponential this. You want to report the odds ratio instead of log odds ratio. You can exponential this coefficient. I think this will give you 0.67, I think, right? So that means that, treatment patients who receive treatment A are less likely to report severe side effects than patients in the treatment B. Again, in JMP, if you wanted to see what exactly is the probability, I can predict. I can using the marginal profiler. So the marginal profiler here, let's just do the see. So here this tells me for the patients who in the treatment group A, the probability of reporting a severe side effects is 0.21 compared to the patient in treatment group B, their probability is 10 percentage points higher. Okay. Again, I don't want to go into the detail, since we have a random effect for the centers, you can turn on the conditional profiler, and we also have the multiple comparisons if you want to do a customized comparison using, two-key and other methods in JMP. And here, this is the same. You saw earlier, you can save the predictions, the average, the marginal predictions, and also the conditional predictions to your data table. Okay. Yeah. So again, so this is the first example. The second, the logistic regression example, version A, using the summarized data, the group data. Now, what if you have the individual data, right? So you have the individual data. So that's my next example, individual data example. This is also from clinical hospitals. So here, our level of the measurements is a patient. So we have a patient, and they are randomly selected from the population, from patient population. So here where the response is binary. 1 means this patient requires intensive care after the surgery. 0 means this patient experienced a routine recovery after the surgery. So it's a 0 and a 1, it's a binary. And we do have the patient demographic information, patient age, and patient post-operative physical status. Again, we're interested in the probability of a patient requiring IC, and we're using GLMM to account for any additional unobserved patient-to-patient variation in requiring IC. We do have, age. We do know what's their post-operative status, but there may be some additional unmeasured variation between the patients. Again, go to the analyze fit model. In this case, I have a binary variable outcome. So here is the post-operative response. And here is my two fixed effects. And so I'm going to switch from the normal logistic, since the normal logistic does not allow me to adding the random effects, right? So I'm going to using the GLMM. So let me see where's, yeah, this is the GLMM. And I have the patient. And I want to model the intensive care, the probability requiring intensive care, which is my target for my interpretation. Hit OK. Oh, let me see. What's wrong? Post. Oh, I should have using this. Yeah. Okay. Here's my results. Again, I'm happy to see this number. It's not, very large. It's close to 1. It's a logit linking function, and this is not significant. P-value is 0.69. I could drop the patient ID, just run a routine, regular logistic regression. But the results will be very, very, very similar. So let me but here are the results. Again, I turn on the indicator parameterization. That will allow me to compare the log odds ratio between a patient whose physical status is good to not good. Age, we see that once age is a continuous variable, so older patients, they tend to have more likely to require intensive care after the surgery. So here, from now on, everything is the same. So I mean, you have the profile, everything. I'm not gonna go to show each of these, but here you can play with that. That gave you the original probability prediction. So this is my second example for the individual level data. Let me summarize. So what I showed you today is a new jump flow modeling personality called the GLMM that allows you to model the counter data or the binary or binomial responses data with random effects. When you should consider using that, and here is the reasons that I gave. And this is our initial release. We only have 2 probability distributions, Poisson and binomial. You're going to expect more features in the future releases, which the JMP Pro 18 will be, I think, released in the springtime next year.